classified collisions as either elastic or inelastic. If you remember, an elastic collision is a collision in which kinetic energy is conserved. Why do we not talk about momentum in the context of an elastic collision? Because momentum is always conserved, right? Momentum is always conserved whether we're talking about an elastic collision or an inelastic collision. The definition of elastic is based on kinetic energy. Yes and no. Kinetic energy is conserved, kinetic energy is lost. What if you find that kinetic energy is gained? You've made a mistake. It's wrong. Now, in the end, we can always determine whether it's elastic or inelastic by doing a calculation, calculating the initial and final kinetic energy. But sometimes we don't need to do that calculation. We don't need to do that calculation if the two objects stick together. If they stick together, we know for sure the kinetic energy will be lost. Kinetic energy will not be conserved. So if they stick together, it is inelastic. Now, if they bounce apart, does that mean it's elastic? No. In fact, if they bounce apart, it is most likely still inelastic. There's probably a 90% chance it's going to be inelastic whether they stick together or not. If they stick together, it's 100%. If they bounce apart, it's probably 80 or 90% that it's still inelastic. But if they bounce apart, you do have to do that calculation. EKI, EKF, and then compare the two. We know that we're dealing with a scalar. So this is the situation. I was talking to you guys earlier today about making sure that you always do the x and the y component, only for momentum, right? If you're dealing with kinetic energy, like we are when we're talking about elastic and inelastic, then we're not going to pay any attention to x and y components. We're not going to pay any attention to negatives. We're not going to pay any attention to funny angles at this point. It's a kinetic energy, and speed are scalars. We're going to just use the values, the magnitudes of the speeds, regardless of the direction. Be able to calculate initial and final, know that the units are joules. We have to stick with standard units, meters per second, kilograms, no components, no funny angles, none of that stuff. Okay, that's it. That's the whole deal, right? Elastic kinetic energy is conserved. Inelastic kinetic energy is not conserved. If they stick together, it's inelastic. If they bounce apart, could be either one. Be able to do the calculations, knowing that we have to use standard units, knowing that we can't cancel things out, and knowing that we never pay any attention to direction, x and y components, signs, funny angles, none of that stuff. And know that, again, momentum is always conserved if it's an isolated system, regardless of whether it's elastic or inelastic. Good? Let's have a look at worksheet number 5, question number 6, which says, refer to question number 7 on worksheet number 4. We want to determine whether this collision is elastic or inelastic. Now, we're going to use the answer that we previously calculated for question number 7 on worksheet number 4. The speed of this 300-gram puck immediately afterwards was 1.07 meters per second, and it was at an angle of 29.7 degrees south of west. We know, though, if we're trying to find whether this is elastic or inelastic, we're not going to pay any attention whatsoever to that angle, right? I didn't even need to write that down. The only thing I need here is the 1.07. Now, do these guys stick together? No, they don't. So therefore, we can't say for certain right now that it is inelastic. But if we had to guess, we're probably going to guess inelastic, right? Because that's what most collisions are. But we want to avoid guessing if we can. Let's calculate EKI and EKF. 1/2 M1, let's call this object number 1 and object number 2. 1/2 M1 V1I squared plus 1/2 M2 V2I squared. This guy disappears because it's stationary, plus 1/2 of M2, which is 0.200, make sure you're in kilograms, times 2.00 squared. It's west, does that matter? When we were doing this question originally as a momentum question, it mattered, right? But now that we're doing it as a kinetic energy question, it's irrelevant, the fact that it's west. 2 squared is 4, 4 times 1/2 is 2, 2 times 0.2 is 0.400 joules. Okay, there's the initial kinetic energy. Let's calculate the final kinetic energy. 1/2 M1 V1F squared plus 1/2 M2 V2F squared. M1 is 0.300, and V1F is 1.07 squared, plus 1/2 of 0.2. This guy's moving at 1 meter per second afterwards. Okay, let's calculate this now. Let's say 0.5 times 0.3 times 1.07 squared. There's the first number, the first term, plus 0.5 times 0.2 times 1 squared. Gives me 0.27, 0.272. There's the initial, there's the final, elastic or inelastic. Inelastic because kinetic energy was off. We predicted that, right? We could have guessed and we would have been right on this, and we are 90% of the time. But like I said on Friday, we want to try to be right 100% of the time, not 90% of the time. If we make a mistake, it's okay, but let's try to get it every time, not just guess so we're right 90% of the time. Yep. No, if they collide and join, you wouldn't have to show any work unless it was a written question where it said, basically prove it mathematically. Okay, but if the question just says, is it elastic or inelastic? No, you wouldn't have to show any work for that. Let's have a quick peek now to finish off the class with practice question set number 6. I think there's only 2 questions here on this, so it should go fairly quickly for us. The first one says, in a classroom demo, 2 identical low-friction dynamics carts are pushed toward each other so that they're traveling in the same speed when they collide. So identical carts, same speed when they collide. Immediately after the collision, the carts come to a complete stop. The teacher challenges his students to describe this collision. Some of the students' descriptions are provided below. So we don't necessarily know whether these descriptions are correct or not, right? These are just descriptions that students provide, which are sometimes correct and sometimes not correct. We want to identify the descriptions that are appropriate for this collision. In other words, the ones that are correct. Which ones are correct? Now, picture this. These 2 carts are coming together. Watch my hands. Coming together, equal masses, equal speeds. They hit each other, and then they stop. So which descriptions are correct? Before the collision occurs, the carts have the same momentum. Do they have the same momentum? Don't they have the same mass and the same velocity? Good. They have the same mass and the same speed. What's momentum? Mass and? Yes. They have the same speed, but opposite direction. So one of them has a momentum of, let's say, 10 this way. The other one would have a momentum of 10, let's say, this way, right? Is that equal mass? Sorry, equal momentum? No, it is not. The momentum is not the same. The magnitude of the momentum is the same, but the momentum is not the same. Do they have the same kinetic energy? Yes, because the direction for kinetic energy is completely irrelevant. So we're going to say 2 is a correct statement. Is this an elastic collision? You know it's either going to be 3 or 4, right? It's either elastic or inelastic. Is this elastic? Do we have to calculate it? Well, in this case, probably not, right? They come to a stop, right? What's the final kinetic energy? 0. What's the initial? I don't know, something. Something is more than nothing, right? So is this elastic? No, we definitely lost kinetic energy there. 2 and 4 is our correct answer. Does that make sense? Number 2. Momentum is classified as a blank quantity, vector or scalar? Vector, yeah. And in an inelastic collision, momentum is conserved. Momentum always stays the same, even if it's inelastic. Kinetic energy is classified as a scalar quantity. In an inelastic collision, kinetic energy is not conserved. So our answer for that one would be A. Good? Oh, there is one more. Question number 3. Holy cow. Look at that. You get a question like this, remember this going forward. We talked about this a little bit, but we see this more often going forward, where we see a lot of information like this. It's almost a reading comp, right? Like it's almost a reading comp question. A reading comp can be hard sometimes But the strategy that you should follow for this, or any other question, really, where you've got a lot of information, is just skim it. Skim the information. You don't have to internalize anything. If you do, then that's great. But if you don't, that's okay. Skim it, and then read the question. And then what should you do after you read the question? It's probably similar to what your English teachers tell you. After you read the question, what should you do? Well, yes, answer the question, but you're going to go back and look in this information again now. Does that make sense? Now we know what we're looking for, right? Let's pretend we skimmed it. Then we'll read the question. The collision that produces a backscattered electron is classified as elastic or inelastic because there is blank change or no change in the kinetic energy of the system. All right. We're looking for something that will tell us whether this backscattered electron is, this collision involving this electron is elastic or not, kinetic energy is conserved or not. So we scroll through here, we're reading it in more detail. Okay, there's all kinds of stuff here that we don't even understand yet. Some electrons from the beam reflect off the specimen at the same speed at which they hit. What does that tell us? If it reflects off at the same speed at which it hits, what does that tell us? Kinetic energy is conserved. Kinetic energy is conserved, therefore it would be elastic because there's no change in kinetic energy. This is the one that if we were guessing, we would have guessed wrong on this, right? That's the point of this one, is to illustrate that 90% of the time, yeah, it's inelastic, but not always, right?